All right, wonderful. Hello, good morning, everyone. We are EquitOx. My name's Estelle. This is Juliette and Ronak. Unfortunately, Caroline and Kevin can't be here with us today, but we're going to be presenting on their behalf and talking to you guys a little bit more about more equitable pulse oximetry. So what is pulse oximetry? Pulse oximetry is a non-invasive way of measuring blood oxygen levels by passing light through the skin at different wavelengths. It's used in a variety of healthcare settings, from emergency medicine all the way through continuous monitoring in the OR. And it's used to evaluate lung function, understand the progression of diseases like COVID-19, as well as just understand your overall cardiovascular health. Particularly in the last 2 years, it's been used to kind of determine who gets life-saving care in resource-limited settings such as ventilators. All right, so if pulse oximetry is so ubiquitous, what does it actually measure? Well, it measures SpO2, which is essentially just a ratio of the oxygenated hemoglobin in your blood. So that would look like this. 3 out of the 4 of these very simplified hemoglobins have bound oxygen, so then you get an SpO2 value of 75%. The way this is calculated is you pass red and infrared light through the skin. The red light gets absorbed by the oxygenated hemoglobin, whereas the infrared light gets absorbed by the deoxygenated hemoglobin. And then you're able to calculate that ratio or that SpO2 value. Now, this is really amazing technology that's done in real time. However, it tends to break down when you're trying to use a pulse oximeter on a person of color. So the red light gets absorbed more by the skin. Thus, you get an overestimation of those oxygenated hemoglobin values, and thus you get falsely high SpO2 readings. You also see an increased variation from 4% to 10% at lower SpO2 values. So what does that really mean clinically, 10% variation? Well, it means if a patient comes in and their pulse oximeter is reading 95%, which is considered borderline healthy, completely normal, their SpO2 could be as low as 85%, and the clinician wouldn't know, and they would have really been needing to do clinical intervention. Moreover, a 2020 study showed that pulse oximetry is 3 times less likely to detect a drop in SpO2 readings for darker skinned patients. And that kind of leads us into our overall problem that we're trying to address, is that this overestimation in SpO2 means worse outcomes for patients of color, as well as higher death rates. And Juliette is now going to talk a little bit about our solution.
Thanks. So our solution is EquitOx, a more equitable pulse oximeter. EquitOx takes a one-time measurement on the tongue for calibration and then performs continuous monitoring on the finger. This one-time tongue measurement helps address racial inequity because the tongue has less variation in pigmentation, and studies have shown that tongue SpO2 readings are actually more accurate than finger readings. Finally, EquitOx is engineered for use in an EMS pre-hospital environment where accurate pulse oximeter readings are often lacking. EquitOx has a bendable silicone clip that can interface with both the tongue and the finger. On one side of the clip, there's a red LED and an infrared LED that shine light that is picked up by a phototransistor on the other side. We also have a display touchscreen with a simple interface that tracks data trends and SpO2. And all of this is in a small, battery-powered portable device. So to use the device, the user will first place the tongue to collect a single reading, and then transfer their clip to the finger for continuous monitoring. This approach calibrates the finger monitoring to the individual and helps to account for some of the inaccuracies of a finger-only approach. And so while our novelty comes from that individual method of calibration, we also want to ensure that the equations that we're using for our device are accurate as well. So to internally calibrate EquitOx, we collect EquitOx sensor readings and SpO2 from a large, diverse data set. And we use that data to develop a linear regression equation between our sensor readings and SpO2 that's used in our device. And so how exactly is EquitOx different than just your standard fingertip pulse oximeter? Well, the standard pulse oximeter generally has the ability for continuous monitoring. It's accurate at higher saturation levels. It's relatively affordable, and it's portable. And EquitOx has those 4 important features, but will also be more racially equitable. It has the ability for trends monitoring, so you can store and display data. It has the ability to take measurements on the tongue. And importantly, it's accurate at lower saturation levels where the most inaccuracy in current data occurs. And so now I'll pass it off to Ronak to talk more about our design process.
Thank you, Juliette. So now I'll be walking you through the process we took to bring our vision for EquitOx to fruition. We initially laid out 8 main steps to achieve through our design process, the first of which was to develop a pulse oximeter akin to current market standard devices through our proof of concept. For that, we developed this device. Pretty rudimentary, pretty bulky, but on the right, we're able to see that the values we were able to acquire were in line with that of a standard fingertip pulse oximeter. We then moved to refine the device, introducing the tongue calibration method that forms the crux of it, as well as improving the form factor to make it more so suitable for that EMS setting we're designing for. This is that improved form factor for the tongue clip. We're able to use a biocompatible silicone material for the formation of the clip. The hardware is all built into the silicone itself, and we're able to use magnets to help keep it secure. In addition, the full form factor shown in the middle here with that minimal viable product is a lot sleeker and more suitable for that transport situation. We're able to use sterile covers shown on the right in order to ensure sanitariness throughout the transfer process from the tongue to the finger. And as we move forward from these physical factors, we move towards that software side, developing an initial GUI in order to have that interfacing with the device. We were additionally able to, upon this level, move towards more of a trends monitoring and statistical analysis. Here showing an uncalibrated measurement from the pulse oximeter, we're able to see that it's pretty high variance, especially compared to the standard that we're measuring against. However, upon calibration, we're looking at much higher accuracy trend lines. This is representative for one patient. And we're able to see that that variance figure drops dramatically from about 6% to about 1.2%, far below that 4% average we were looking at earlier. In addition, ANOVA testing showed that the mean was insignificant before, whereas off by about 1.9% initially. So from here, we move towards refining our device for that final prototype. We move towards dye testing in order to ensure that we're able to really perform at low sensitivity analysis, as it's unethical to test below 90% levels of healthy levels of pulse ox in healthy humans. We were able to work with our faculty mentor to design a dye proxy system in order to effectively try and test this. Using known values of hemoglobin, we were able to emulate what a hypoxic patient's blood would look like and then test our device against it. With this, we were able to verify that the most sensitive part of our device, most likely to fail, was the red sensor, and it was still able to hit limits of quantitization at 60% SpO2 readings. For context, below 80%, we see vital organs start to fail, and below 70% is almost deadly without immediate intensive medical intervention. So we're really able to accurately encompass the entire range of potential human SpO2s, whereas current devices do fail around that 85% mark and below in accuracy. And from there, we have our final prototype. It's entirely independent. We have ports for developing data off to the hospitals. The final GUI is shown on the top screen, and it all fits in quite nicely. We're happy to show it to you later at the design presentation. But for now, we have this video to demonstrate the prototype. So see here a patient on the right, an EMT coming in on the left. They're handed the device to place on the tongue. Once it's placed, the EMT presses a button on the device to get the calibration reading. And just like that, it's already calibrated. The sanitary covers are then taken off, and the device can be transferred to the finger for continuous monitoring. Great. And that concluded the development of our final prototype. Now, moving forward, what do we have to do? So first, we'd like to really expand out our user and stakeholder feedback. We have got in contact with EMTs from Merton. Over 60 have indicated willingness to use our device in field and provide feedback. In addition, we've started to do impact analysis within hospital settings, and through that have gotten several testimonials, one of which is here, really showing that in that pulmonary field where pulse ox is used every day, that clinical significance truly is there for achieving this device. Moving forward, we additionally want to refine our device for full-scale manufacturing through having printable circuit boards and integrated circuits to really scale that form factor down, as well as developing manufacturing partnerships. Funding for this will be provided at least through June of 2023 through the Berkman Fund, which we're happy to say we received this morning. And that'll help us as well with moving towards a final stage of clinical testing. Any non-over-the-counter pulse oximeter requires clinical testing through to get FDA approval. And so doing that through IRB-approved trials would be beneficial, as well as working with Dr. Atkins, a partner in our sleep apnea lab, to ethically test low SpO2 in patients. And with that, that concludes our presentation. So thank you so much for listening to us, and we're happy to build a more equitable future with you today. Thank you.
You guys have any questions?
Just a design question on the, I know you spoke to the field about the EMTs who collect with office. Is your product also potentially looking at maybe being a personal device? Because, you know, you're putting it into your mouth. I'm just wondering if you've done any, you know, understanding of patients who might not want that.
Yeah, certainly. It's outside of the initial scope of where we designed it for, but absolutely that application exists. And we're able to justify that through the cost analysis we've done. The device cost production in its current form is about $40, but once we move towards the PCB and final design prototype, that we should see that cost drop dramatically, estimated at about $16, which would be competitive against over-the-counter pulse oximeters, which currently range around 30 to 40. So it is certainly feasible. Yeah. Thank you.
Great presentation, you guys. I had some questions about kind of what thoughts you had on failure modes for the device with respect to your design process. Like things that came up for me, I was like, how would nail polish affect this? You have these sterile covers. What if they bunch up and affect the measurements or like positioning on the tongue? And I was curious if you could speak to how you've, I guess, thought about those different modes of failure.
Yeah, here, I can start with that. So nail polish is actually one of the more interesting fringe cases we've looked at. Other ones being like drinking Gatorade or like having a popsicle and stuff like that that can really affect that pigmentation. I think fortunately, since with working on the finger potential confounding variables, our calibration method does certainly account for that. Since we know the accurate measurement, then we can adjust for any sort of pigmentation that can occur through nail polish. The other way around is a little bit more variable. But as of right now, we've not seen significant indications that it has a problem within the testing we've done so far. And
then I think your like second part of that question was with regard to like the sterile covers as a failure mode. So we did do statistical testing to make sure that like with and without the sterile cover, there was no differences between our readings. Yes.
Thank you.
Yes, of course.
Any more questions? Yes.
Also wanted to say great presentation. I thought you brought us through the process very well with images and videos. I had a question about that 10% variance. How much of that do you think is due to the device versus your linear regression and some of the data set that you mentioned you calibrated it with?
So that 10% variation for like darker skinned patients at lower SpO2 values is actually compared to arterial gas, which is a direct measurement of SpO2. So that's like just like there's been quite a few clinical studies within the last few years that just have pointed out that even standard pulse oximeters that are used for continuous monitoring in the hospital have that 10% variance. Compared to like direct measurements like arterial gas. And so that's what we were aiming to address with this.
I guess, sorry, I can rephrase that.
Oh.
How much of the device addresses that 10%? How much of it is the linear regression on the calibration model?
Oh. Okay, Juliette, do you want to take that with regards to the calibration? Or Ronak?
Maybe.
yeah, our device is able to ensure fair accuracy. I think going back to that uncalibrated, calibrated chart we saw, we're still reading, I think it was about 6% variation with the uncalibrated readings. So accounting for that 10%, assuming that's representative of our full data sample, it was one section. There's about a 4% accountability for the device versus another 5.5% for the calibration method. Yeah.
That's all the time we have for questions.
Thank you, everyone.